Hello everyone, hope everyone is doing well. Today we're going to learn about one-tailed tests. So far we have done in the previous videos, we have done what we call two-tailed tests, where we had a null hypothesis, which basically was whatever the status quo was and whatever was given to us from maybe historical studies. And we are basically, and the alternate is that the null hypothesis is not true. Now, in two-tailed test, what we used to do is we would assume that if supposing we had a distribution like this, a normal distribution of the sample means of that population, if it were a two-tailed test, then we would have two critical values, two cutoff points like that, and we would note that since 95% of the sample means are within this range, so any mean that is on this side, we allocated 2.5% on each side. Let's say if we were doing an alpha of 0.05, critical value of 5%, then we would say that 2.5% are on each side of the distribution, and hence the name two-tailed test. That means if our values fell in either of those two tails, then we would reject the null. However, we also have what we would call one-tailed tests. And since there's one tail to the left and one tail to the right, so we have something called a left-tailed and also a right-tailed. Now, what does that mean? Well, that means that in some cases, we may not just want the null or the alternate showing that the null is not, or the alternate is showing that the mean is not equal to a certain value. We are still testing the population mean, but what we are doing is we may say that if the numbers are basically greater than a certain value, then it's fine. So if this is my mean of some number, let's say 20, then one-tailed test says, let's say if I'm doing a left-tailed test, then if any number is on this side, we reject the null. But if any number is anywhere on this side, including the extreme of the right tail, we say do not reject. So this is one type of tailed. Right tailed is showing here. This is actually a left tail test. On the other hand, a right tail would be, let's say everything, we may want everything to the left to be, if the value falls within any numbers to the left, we do not reject the null. But if it falls after a certain critical value to the right, in this case, we reject the null. And all this means, if the value falls anywhere here, we do not reject. And this is called a right-tailed test. Now we're going to look at some examples that shows us why do we use a left-tailed test or a right-tailed test, and what benefits they have, and what are the steps. The steps are basically the same thing as before. So the first thing we would do is come up with the null and alternate. And then the second would be, collect the sample. And then we would, in the third step, we would find the Z or the T statistics, depending upon what we are trying to do. If we have the population standard deviation is known, if sigma is known, we use the Z values or the Z stat. If sigma is unknown, then we use the T stat. And so based on whether we know the sigma or not know the sigma, we will use either the Z stat or the T stat. And then the fourth step is find the critical value of Z or T. And then in the fifth step, or then after we have our Z stat, we compare it with the critical value, and then we know whether to reject or not reject the null. So let's look at some examples. Let's say we have, our first example is this. We have maybe a bank branch where the mean waiting time for customers is 5 minutes and the standard deviation is 2 minutes. So from here, we know that in our case, this number is the mean, population mean, and this number is the population standard deviation. So we already have the mean and standard deviation of the population. Now, in order to reduce the wait times, the bank implemented a training session. And then we collected a sample of 35 customers. So this would be my N. And the waiting times were measured. And the mean waiting time is 3.8 minutes, which is my X bar. And the sample standard deviation is 1.8 minutes, which is my S bar. Now, since the population standard deviation is known, we should be using the Z-stat. But the first thing is, step 1 is state the null. So in our case, let's write the null and the alternate. So in my case, the null hypothesis here is going to be that we already have it at 5 minutes. That means if we did not do the improvement, the mean would have been 5 minutes. So anytime, if we have a mean of 5 minutes, since we want to reduce the time, so if I have greater than 5 minutes, that's bad. At least that's not what my aim is. I want my aim to be that the waiting time should fall to less than 5 minutes. So then my null would be, the status quo is basically it is 5 minutes, so the mean waiting time should be greater than or equal to 5 minutes. And since the alternate is after the training, we want to reduce the waiting time. So the alternate is the mean waiting time is less than 5 minutes. Or in other words, if I were to write this in terms of, let's say if I were to write it in notation form, I would write, so in the case of null hypothesis, I would write that mu is greater than or equal to 5 minutes. And my alternate then is that mean is less than 5 minutes. So again, just to recap, we always test the population mean. So our null hypothesis is always testing whether the population mean has changed. So it's always going to be mu instead of X bar. Now in the second step, we are going to collect the data. So I know my X bar, that is going to be 3.8 minutes. I don't need S bar since I have sigma, which is 2 minutes, and I have N, which is 35. And then my third step is to find the Z or T value. Now in our case, we are going to find the Z statistics because since the population standard deviation is known, so we can use the normal distribution, so the Z statistic. And so our formula for Z stat is X bar minus mu divided by the sigma over square root of N. So let's calculate the numerator and the denominator. So the numerator is going to be 3.8 minus 5. Denominator is equal to 2 divided by square root of 35. So we get those numbers. So then my Z stat is just the numerator divided by the denominator, so which comes out to be those numbers. So we have a Z stat of negative 3.54. Now in our case is step 4 is find the critical value. Now in our case, we don't have to deal with 2 steps, or we don't have 2 tails to deal with. So our critical value will just be norm.s.inv and the probability. Let's say we are testing it at alpha equals 0.05. So we have that number. All right. Now we have this as our critical value. Now the question is, are we doing a left tail test or a right tail test? So let's go and check before we solve for this. And this is where it becomes important to draw the normal distribution. So let's say this is my mean. Now we want to see, let's write our null here. Mu is greater than or equal to 5 minutes, and my alternate is mu must be less than 5 minutes. So if this is my mu, which is 5, If the number falls below 5, then that's great. Now, that means that any number below 5 is good, but we give a little leeway because, as central limit theorem showed us, that even if we collect samples from the population, sometimes we may have sample means that are less than 5, and so we'll give a little leeway. That means that our alternate should be somewhere here. So let's say this is the critical value. Then any number to the right, all this number, we do not reject. But here we reject the null. So thus, my critical value that I just calculated should be negative 1.64. And so if my z-stat falls anywhere in this region, I should reject the null. And so we would call this the left tail test. So in our case, we have, again, it's easier just to use the absolute values. So the absolute value of z-stat is greater in magnitude than the absolute value of the critical value of z. So we reject the null, which means that the waiting times fell. So the waiting times have fallen. So in this case, if you notice, we are not dividing the alpha by 2. Since it's a one-tail test, we are keeping the alpha as is. Now the other way of doing this same thing is using p-values. So instead of z-stat and comparing it with the critical value, I can convert this number to a p-value. So what I can do here is I can just write the p-value would be equal to norm.s.dist, and then I would take that z, and for cumulative I would say is true, and I get a p-value of that number. Now, in my case, if the p-value is less than alpha, we reject the null. If the p-value is greater than alpha, we do not reject. Here, in two-tail tests, we actually multiplied the p-value by 2 because you could fall on either side of the tail. Here, we're just falling on one side of the tail. So I see that the p-value is less than alpha, which is 0.05 in my case. So we do not reject, or we reject the null. Either way is fine. We can either use z-stat and compare it with the critical value of z, or we could convert the z-stat to a p-value and then do that test. So here is one example of using this. So we used left tail test, or some people call it a lower tail test, to do our testing here. Now let's look at maybe what we want to do is a right tail test. Now let's look at this example. A school wants to see if a new testing format can increase test scores. So before the test changed, the mean score was 75. Now after the test change was implemented, we took 60 students and the mean score is 82. So then we know that this is my mean, population mean. I don't have the population standard deviation given to me, but I have n, I have x bar, which is the sample mean, and I have s bar, which is the sample standard deviation. So let's test if the format change increased test scores. Now first we need to write down my null and alternate. Let's say we are testing it at 10%. So let's say alpha is 0.1. So we're looking at here that initially our mean score was 75. So if I were to draw it, then this is what my mean score is. Now I implemented some testing change, and I want the mean to move rightwards. And so I find that, again, if I go up to a certain level, that's fine. It may still be equal to 75. But beyond this, I would say that the population mean is no longer 75. So then my null would be that the population mean is in this region. And once I cross the threshold, this is where I should reject the null. So this is my one tail test. This is going to be a right tail test or a upper tail test. Some books write it as right tail, some books write it as upper tail. So in our case then, if I were to write this up, so in my case, my mean is now going to be, so my null hypothesis would be that the mean is going to be less than or equal to 75. And so I want the mean to increase, so the alternate is it is greater than 75. So that is now going to tell me that anywhere I land in this side, I should reject the null. So we have our null and alternate hypothesis. I did not write it out in full. I can use symbols now. So my population mean, if it remains at 75 or less than 75, I reject the null. If it's greater than 75, then I do not reject the null. So this is my step 1. Now step 2 is calculate or find the sample averages. So I know my x bar is 82. I know my s bar is 2.4 and n is 60. So I have all this information. Now my step 3 is calculating the z or t-stat. Now in my case, I don't know the population standard deviation. Population standard deviation is missing. I do know the sample standard deviation, which is 2.4. So we are going to use the t-stat here in our analysis. So this is my t-stat, which is x bar minus mu divided by the s bar over the square root of n. So let me find the numerator first, which is going to be my x bar is 82 minus population mean is 75. And the denominator, that is going to be, so that's going to be my numerator and denominator. So my t-stat is, so that is my t-statistics. And the next step is find the critical value of t. At alpha, as we said, alpha is 0.05. Or no, we said alpha is 0.1. So let us write alpha equals 0.1. So in that case, I would just do t dot inv. The probability is 0.1. Degrees of freedom is going to be 60 minus 1. Since I have n is 60, I subtract 1 from it, and I get a negative value. But what I can do is, in my case, since it is t distributions are symmetric and we have, let's say it's going to be a right tail test, we actually just found this number, which was negative 1.29. Yes, negative 1.29. But we need actually, since we are testing it at the right tail, so we need this number. Since it's a symmetric test, we can just write 1.29 and eliminate this. So therefore, if my value falls anywhere, my t-stat falls anywhere here, we reject the null. Now, in my case, I will write that, so the t value should be negative that, just to make it easier, so that we are not dealing with a negative value. In this case, we don't need to write absolute value or anything because we know the number, so we can write the t-stat is greater in value than the critical value of t. So we reject the null. The test scores improved. So now we can say that since this t-stat that we calculated is greater than the critical value of t that we have down here, we will reject the null, and we can now say that the test scores have improved. Similarly, I can find the p-value for this instead of t-values, or instead of finding the critical value of t. So what I can write is, instead of doing critical value of t, I can write p-value. That would be equal to, now in this case, I would say that's my x. The degrees of freedom is going to be 60 minus 1. Cumulative, it is true. And I get a huge number. Now that doesn't make sense. Why is that? The reason is, well, as we said from before, the t-values measure this number that we calculated. Excel measures it from left to right. So if this is my t-value, it will measure this area. Since my value is very high, it's 22, so it's going to measure this area, and so it's very close to 1. So there are two ways we could find this t-value. One is if I actually did 1 minus the t-distribution. That is one way of doing it. Or the other way would be if I actually did t.dist.rt, and I wrote the x, which was this value, 22, and the degrees of freedom is 60 minus 1. And I get a very small value, which is very close to 0. So either one is fine, but if you're starting to study statistics, I would just use one formula for everything. That's why I don't use t.inv.2t or anything. I just use just one formula to use it. But you can use this, but this is also fine. And here we see that, well, the p-value is less than. So our p-value is less than alpha, so we reject the null. And this is how we write our null and alternate hypothesis and then evaluate it at a different critical value. Hopefully this was helpful, and I will see you at a later lecture. Have a good day. Goodbye.